Hello, this is Mr. Gilmore with the 4.6, the angle side, hypotenuse leg, and converse of ITT lesson. Today we're going to add the last two triangle congruence principles. As spoken before in Chapter 3, we mentioned that there were a total of 5 triangle congruence shortcuts. We saw side angle side, side side side, and angle side angle then. But now thanks to Tasty, we can add our last two, which is angle side and hypotenuse leg. We're going to find that hypotenuse leg is a special case that involves a shortcut to congruence. To finish the lesson off, we're going to talk about the converse of ITT. We saw back in Chapter 3 as well that to prove the isosceles triangle theorem, we needed congruence of side angle side. Well, now with the use of angle side, we can then prove the converse of the isosceles triangle theorem, which again we'll see at the end of the lesson. Let's jump into our last two triangle congruence statements. So remember, these congruence principles are shortcuts to congruence. AAS is short for the angle side. We're going to find that the side in this case is not included, meaning it's not between the pair of equal angles. And then HL stands for hypotenuse leg. Now we only see that vocabulary when we talk about triangles, specifically with right triangles. So we'll talk about the special case of right triangle congruence with hypotenuse leg. Let's start with the angle side. This is the conditional. We'll see the setup of the proof on the next slide, and then we'll follow up with the proof on the next. So if two angles of one triangle equal two angles of another, and a pair of non-included sides which correspond are equal, then the triangles are congruent. See, the one thing that's tricky about the angle side is that since we have this pair of non-included sides, we have to make sure that those non-included sides actually correspond with each other. Remember how we think about congruence. It's producing a list, which means when we produce the list for each of our two triangles, the pair of non-included sides must be in the same position. If they're not in the same position, that means they do not correspond. So it can't just be any pair of non-included sides. They must be a corresponding equal pair of non-included sides. Let's take a look at a diagram. So here's our setup of the proof, angle side. The proof for angle side is actually dead simple now, thanks to Tasty. And in reality, it's really thanks to Tasty and one of its corollaries. So let's talk about our setup. We're given two triangles, ABC, and triangle RST, such that we do have two angles of the first equal to angles second. Angle A is equal to angle R, angle C is equal to angle T, and then we are given a pair of non-included sides which are corresponding. BC and ST correspond with each other, and we're given those as equal. Let's then prove that these two triangles are in fact congruent. So how are we going to do that? Let's take a look at the proof together. So our diagram is still above, given that, remember, A and R are equal, C and T are equal, and that our set of non-included but corresponding sides, BC and ST, are equal. So it's a three-step proof. It's very simple. Here's why. We can, from this, claim that angle B and angle S are equal to each other. Why? Well, this should actually come right from one of the corollaries we saw from our last lesson. If two angles of one triangle are equal to two angles of another, then we can claim that the third angles are also equal. This is the third angles theorem. By the third angle theorem, we know that those two angles, angle B and angle S, have to be equal to each other because of Tasty. Now, what does that do for us? If I were to mark then angle B and angle S is equal, notice that it changes the dynamic of our two triangles. Now we know that two angles of one triangle are equal to angles of another, and the pair of included sides are equal. Notice how we made BC and ST now included between the pair of equal angles, which means we can claim triangle ABC and triangle RST are officially congruent by angle side angle congruence. So there we have it. There's the proof of angle side. Let's now talk about the hypotenuse leg, which is our last case for shortcut congruence, but it's our last special case because we're going to see that we're specifically dealing with right triangles. So let's take a look at this conditional. If two right triangles, so that's actually one of the criteria that goes into the hypotenuse leg, is the two triangles have to be right. So if two right triangles have equal hypotenuses and a pair of equal legs, then those right triangles are congruent. Now, if you recall, back in Chapter 3, we talked about that our shortcut to congruence involves 3. Now, the title of our principle, HL, it implies there's only 2, but we have to think about what the conditional state. There really are three criteria that goes into it. Number one, they have to be right triangles. Number two, we have to have an equal pair of hypotenuses. And number three, we have to have an equal pair of legs. So there's our magic number 3. It's just in the title, HL, we can then infer from that they must be right triangles, which is our third criteria. So if two right triangles have equal hypotenuses and a pair of equal legs, then those right triangles are in fact congruent. Let's take a look at the setup of this. So if, and here's our diagram, triangle ABC and triangle DEF are both right triangles, their hypotenuses are equal, AB and DE are equal, and a pair of equal legs we have a pair of equal legs that are equal, BC and EF, then we can claim these two triangles are in fact congruent. So we're actually going to take a look at a proof overview. I'm not going to walk through the entire proof of this because when we jump over to the worksheet, you're going to see the proof of this is guided. So how are we going to tackle this? Well, we're actually going to take a little page out of a book we saw back in chapter 3, which was, let's build a third triangle to then show that the third triangle is congruent to each of the two given triangles here. And if we have two triangles that are each congruent to a third, then the two triangles must also be congruent to each other. So we're going to strategically build a third triangle. Let's see how we build this third triangle on the next slide. So we still have triangle ABC and triangle DEF. Those are our two given triangles, such that they're right triangles, that we have equal hypotenuses and an equal pair of sides, or it's an equal pair of legs. So what are we going to do? Well, here's what we're going to do first. We're going to measure the leg of triangle DEF. We're going to measure this side here, DF. We know the ruler postulate says we can measure. Well, we can also make measure. How are we going to do this? We're going to then take our segment AC and we're going to extend the side out to a point Z such that CZ, if you notice, is equal in measure to our side over there, DF. With then one of our last constructions, now that we have this new point Z, let's just simply connect point Z to point B. Now we've formed a third triangle. So here's actually what we're going to prove. Now, again, I'm not going to do all the specifics to the proof because it's going to be guided on your worksheet. But let me give you a breakdown of what you're going to see. Let's call these two triangles here triangle 1, triangle 2, and triangle 3. The very first thing that you're going to do is that you can prove that triangle 2 is congruent to triangle 3. Very simply, you can find that there are two sides and the included angle of one are equal to two sides and the included angle of another, which means we could prove that very quickly with side angle side. The next thing we're going to do is we're going to also prove that triangle 1 is congruent to triangle 3. Now, how we get to this one is all thanks to now one of our newest triangle congruence principles, angle side angle. So you're going to prove that with angle side angle. And you'll have to then set up some of the information in order to show that you have, not angle side angle, it would be angle angle side. You're going to show that you have two angles of one triangle equal to two angles of another, and there is an equal pair of sides, okay, an equal pair of non-included sides that correspond, that those two triangles will then be congruent. And once we've arrived at that conclusion, then we can say triangle 1 is congruent to triangle 2, all because of the transitivity of congruence. And so you'll see on the worksheet a breakdown of the entire proof where I give you the statements and you fill in the reasons. All right? Now, you might be wondering, isn't that, when we just proved the hypotenuse leg, isn't that angle side side? And students might protest, wait, Mr. Gilmore, angle side side doesn't work. There were counterexamples to it. But my response to that would be, my good students, it does work if the angle is right. So if the angle is a right angle, then yes, this is the good angle side side. It's the only good version of angle side side in which you do have triangle congruence. Now let's move on to our last theorem for today's lesson, the converse of ITT. Let's juxtapose the two conditionals of the ITT and the converse ITT. So remember, a converse is the exchange of the given and conclusion. Let's read the original conditional for ITT. It says that in a triangle with a pair of equal sides, then the angles opposite those equal sides are themselves equal, which means if we're given a pair of equal sides, then we concluded with a pair of equal angles. Well, the converse then is the exchange of that given and conclusion. So the converse ITT then says this, that in a triangle with a pair of equal angles, the sides opposite those equal angles are themselves equal. So the converse then states, if we have a pair of equal angles, then we have a pair of equal sides. Let's jump then into the setup of our proof and take a look at what the proof then would be. So here is our triangle ABC. Now I can't call this triangle isosceles. I don't know that there are two sides that are equal, but I can prove that it's isosceles given the fact that angle A and angle C are equal to each other. So here we have triangle ABC with a measure angle A equals to measure angle C. Let's prove that the two sides AB and BC are equal to each other. So I'm going to go ahead and set up my two column. So where I begin is with my given triangle ABC with the measure of angle A equals the measure of angle C. Now let me go ahead and give the punchline away. We're going to use triangle congruence to help us prove the converse of ITT. So where do I begin? It's actually an identical step to where we began with the ITT. We're going to bisect the third angle here. So we're going to take angle B and we're going to bisect it, meaning we produce this segment BD such that these two angles produced here at the top are actually going to be equal to each other. So we're going to say here in my proof, BD bisects angle B. And we can then toss that into our construction reasoning. Well, where do we go from that? Well, we know that angle bisectors cut angles in half. Let's state that equal pair of angles. So the measure of angle A, BD is actually equal to the measure of angle CBD. And that is, of course, by the definition of angle bisector. Well, where do we go from there? Well, when we bisect that angle, we produce this side BD. As it turns out, that now cuts our entire triangle ABC into two smaller triangles, ABD and CBD, and those two triangles have a common side. So here in step 4, let's use that common side to state that equality. BD is equal to itself by our good old property of reflexivity of equality, and what that then produces are three pairs of equal things. We have already given to us angle A and angle C. We found by our angle bisector ABD and CBD, and there's a common side, which means we have enough to declare triangle congruence. Triangle ABD is in fact congruent to triangle CBD by our very new principle here, right off the line here, angle side congruence. What can we do then with congruence? We can invite our very best friend to the party, which is CPCTC. So what is it that I'm going to conclude that I know about these two triangles? I know that they have an equal pair of sides that correspond, AB and BC. So thus, given a triangle with two equal angles, we know the sides opposite those two angles must also be equal, which again is the proof of Converse ITT. So that concludes today's lesson 4.6. This actually concludes the very last lesson of our chapter, which means you'll be getting a chapter test review to actually cover over these last several sections. Please be sure to work on the 4.6 worksheet. If you do have any questions on it, do not hesitate to email me. Be good and do good.